And the second talk of this morning session is by Lenny Ng, and this is the second part of the mini course, not contact homology, string topology, and topological strings.
All right, thank you. So just to recap where we were, so I talked about Legendre and contact homology yesterday, so let's suppose that we have a contact manifold, which is in particular a one-jet space, and lambda is a Legendre manifold inside here. So out of this we get this Chekhov-Eliashberg differential graded algebra generated by ring chords. And the differential, remember, counts holomorphic disks. So there are holomorphic disks into the symplectization R cross V with boundary mostly on actually all on the Lagrangian cylinder over lambda, and the image looks something like this. So this is the R direction here. And so a disk like this will contribute a term, so let me color code. So these bits of the boundary are all lying on this Lagrangian cylinder. And this particular set of holomorphic disk, if it's rigid, it'll contribute a term so it contributes to the differential of AI, the term. So there's a plus or minus that I want to ignore, but the sort of the key things are the homology class of this this disk. So we think of this as inside of relative H2 of V relative to lambda. So just project out the R direction, and then the product of the wave chords at the bottom. So the differential of this thing at the top is the product of these things at the bottom, and this is for k at least 0. So there's actually a case where k is equal to 0, and then it just contributes. So that looks like a disk with no positive end, and that will just contribute something inside of the coefficient ring, which I didn't say what it was. So the differential graded algebra over z brackets relative to h2 of v lambda. And then, so then the homology of this, and I will continue not saying anything about the grading. So the homology of this differential graded algebra is called the Legendre contact homology of lambda. Legendre contact homology. So this is the general setup, and I want to emphasize one particular case. So a special case, the one that we'll mainly be interested in, is where, so V is the unit cotangent bundle of R3, and lambda is the conormal of something. So lambda is the conormal sitting inside of here, a unit conormal. Where this is the unit normal to k. So remember, I drew a picture last time where here's T star. Oops. Here's the disk part of the cotangent bundle of R3. Here's its boundary. Again, if the non-compactness of R3 makes you upset, you can just replace that by S3 for most purposes. And then here's the zero section, and here's the conormal to K, which is Lagrangian sitting inside of the symplectic manifold. It intersects R3 and K, and then this would be better. Oh, well, okay, I think this is fine. So it's where it hits the boundary is lambda K.
Well, by the way, you said that if you can replace R3 by S3, Can it produce new record?
That actually can produce new, well, more disturbingly, it will produce new rib orbits.
Yeah.
So this is, when you do S3 instead of R3, you come outside of this class of one-jet bundles. So you're correct. So in fact, I sort of want to deal with R3, but at some point I'm going to switch to S3 and without comment. So there is a technical way you can get rid of the closed rib orbits through some augmentation. Right. So in this case, so then this definition, the Legendre contact homology of lambda k is called the not contact homology okay. And this is then an invariant. Oh, I didn't say what k was, right? So k is an honor link. This is now an invariant of the smooth isotopy type of K. Okay. And so I want to talk more about this in a little bit. Let me just say that there is an open question which I think used to be more interesting than it is now, which was, does this completely determine K? Okay, so I'll explain why this is not so interesting anymore. Okay, so this motivates what I wanted to talk about today, but I realized that because of the pace that I'm going at, maybe I should actually try to just turn what I was going to talk about today into a sort of an extended remark, so I can then get to talking about augmentations, which is something I want to spend more time on. So here's some sort of extended remark. So remark. This remark will go on for a little bit. So we can, there's a way to enhance this invariant. This invariant through some sort of stupid trick, which is just to add a little bit of extra information into this picture. So let's P be a point in R3, but not in K. So then we have, so to K we have this conormal lambda K. I'm going to be assuming for a bit that K is, so say that K is a knot. As opposed to a multi-component link. Okay, so K gives this conormal, which is topologically a 2-torus. But the point P, so this sits inside of the cotangent, the unit cotangent bundle of R3. The point P itself also has a conormal. So what is the conormal to a point? It's actually just the fiber or over that point. So lambda P, and this is the cotangent fiber. So it's an S2 over the point P in this unit cotangent bundle. Okay. Okay, and these two things are disjoint. Okay, so they're both Legendrian. This is Legendrian. This one is also Legendrian, and they are disjoint because P is not. It does not lie in K. And then we can consider. The Legendrian contact homology of not just this single component torus, but the union of that with this cotangent fiber. So this is now a 2-torus union with a 2-sphere, and it's Legendrian, and through this usual process, then we get some sort of differential graded algebra with the homology. So here's a theorem. from, I guess, last year. Last year is no longer last year, 2 years ago. It's still January, right? I can make this mistake. From this thing, plus a little bit of additional data. So I'm going to not say much about this, but plus. So this is some sort of homology. There's an additional multiplicative structure on it that's extra. So an extra product structure. And this product structure actually, so Legendrian contact homology counts these homomorphic disks with one positive end at a wave chord. And this product structure counts disks with two positive ends. This is a little bit of a nervous-making thing to do because sometimes the moduli spaces don't degenerate nicely. But in this particular circumstance, there's some old work of Tobias Ekholm that says that it's okay, essentially because there are two different components from two positive puncture disks. We can recover K. So that is to say, you can the type of the knot K is completely determined by this algebraic information. And I'll say something about the proof of this, but this is the thing that I'm going to massively compress. But let me say that a corollary of this is that the Legendrian type, the Legendrian torus lambda K, completely determines K. Yes.
When you have several positive punctures, yeah?
Yes.
What is it on homology? Because it's some part of negative puncture in some part.
That is correct, yes.
Yeah, because it reminds me as it's all very Calabi structure. It means it's again some inputs and outputs.
That's right.
It's the same story.
Yeah, that's exactly right. Yes. Although in this case, we restrict it so that the two positive ends are actually next to each other, so they occur consecutively. Okay, and why is this? So this is just because this actually the cleanest way that I can say this really uses the fact that we're in R3 and not in S3. So after I sort of muddied the waters with that, I actually do want this to be in R3. So the point is that the reason for this is if K and K prime are knots, and lambda K is Legendrian isotopic to lambda K prime, then the same thing is true if you add in this fiber, cotangent fiber. Assuming that P is not on either of the knots, is Legendrian isotopic to lambda K prime, union with lambda P. So why is that? That is because whatever the isotopy is that takes you from here to there, it has compact support. So inside of R3, so just pick P to be outside of that compact support. So since R3 is not compact, you can just pick something that lies away from there, and then it's never touched by this isotopy, so you might as well just throw it in. Okay, and once you have that's true, then that means that this thing that I defined here is an invariant of K, of lambda K. And since this completely determines the knot, then that means that lambda K completely determines the knot. Okay, and this also explains why maybe this open question is no longer so exciting. I should say maybe the relation between this enhanced invariant and non-contact homology is that non-contact homology is a quotient of this thing. So you just quotient out by all wave chords that have at least one endpoint on this particular component.
Here you use probably some difficult results with topology. Because you need again something to directly say you maybe
Yes.
specifically use some other people results.
You do use some results. So the result, I'll mention this, but the result that you use is just that the group, the fundamental group, along with the peripheral subgroup, determines the knot. Okay, so yeah, so maybe I should say a little bit about how this is proven. I'll actually tell you how this is not proven. This is not actually the proof, but I think it's somehow more illuminating than the actual proof. So I think this is some sort of strategy for proving this, and it's not actually what we do, but it's somehow a little bit nicer to draw. Maybe it's slightly more interesting for this audience. So let me draw that picture that I drew over there again, but now I'm going to add in some stuff. So here's this cotangent bundle R3. Here's its boundary, the unit cotangent bundle. And now I should realize the color. Let's see. So here is R3. So what I'm drawing right now is what I drew over there. So this is the knot inside of R3, and it's co-normal, and that intersects the boundary in this Legendrian lambda k. And now we have this additional point P, and its cotangent fiber, it's a little bit hard to draw, but it looks a little bit like this. And the cotangent sphere over P is lambda P up there. And maybe I'll give this name, this cotangent fiber, a name F. So let's say that F for fiber. So let's write F to be the fiber, cotangent fiber of P in the disk cotangent bundle of R3. So this is a Lagrangian, and so now what we have here is we have this picture. There are 3 Lagrangians in this picture. The 3 colored things are all Lagrangian. Okay. And then the proof, which is not actually the proof, is to consider partially wrapped Floer homology for we're going to apply it to this fiber here, but the partial wrapping, the wrapping is stopped by this Legendrian at infinity, so stopped by the Legendrian on the boundary, which is so let's see. So then one can check the following things. So the first thing is that partially wrapped Floer homology. Let's take the partially wrapped Floer homology of F with itself, of just F. So this is determined so it's determined by some stuff at infinity. It's actually determined by this enhanced invariant that I wrote down before, lambda k union lambda p. You can check this. So on the level of generators, this is not too hard to check. You can just sort of check that. Well, the generators actually are wave chords of lambda p, but in some sort of weird perturbed contact manifolds, and they correspond to concatenations of wave chords of this Legendrian link. For the fact that the differentials agree, there's some sort of argument that this is what we did not do. There's an argument that follows bourgeois, bourgeois surgery formula. I will say a word about, in a second about what we actually did do, but this is sort of morally speaking what was going on. Oh, and I should say that this additional product structure from the twice positive punctured disks, that corresponds to the pair of pants product on this partially wrapped thing. Okay. Okay, so that's claim number 1. And then claim number 2, if you take the, so I've been convinced that my original grading conventions are wrong, and now I think of this as degree 0 wrapped Floer homology. This is actually, with the product structure, it's isomorphic, ring isomorphic to the group ring of the complement of pi 1 of the complement of K. So this is the knot group of K. So this shouldn't look completely weird. I mean, this is some sort of relative version of the wrapped Floer homology of cotangent fiber in the cotangent bundle of some manifold n is Q, n is the cohomology of the free loop space of n. So this is some sort of relative version of that. Or that's at least in my head how I justify that this makes some amount of sense. Okay, and then the third step is the one that I mentioned. That okay. So once you have this, then you can recover the group ring of pi 1, and then there's some classical arguments. So there's some amount of algebra, and then some argument of Waldhausen. Well, okay. So the first thing you'd say is that the group ring of a group doesn't always determine the group itself. But it does in this case, in the case where the group is what's called left orderable. So this determines by 1 of the knot complement. And then by we need a little bit more than this. So pi 1 of the knot complement also doesn't necessarily determine K, but it does if you also have, so along with, so there's additional information in the picture that I'm not going to talk about, which is that there are 2 particular classes in pi 1 that are important, which are the longitude and the meridian of the knot. So I'll write these as L and M. And somehow you can track through using coefficients and actually figure out where inside of here are the longitude and meridian. So what this tells you is that from this picture that we have, we can recover the group ring of the complement of the knot. We can recover the fundamental group of the complement of the knot, along with the longitude and meridian, and then there's a result of Waldhausen from the 60s that says that this determines K. Okay, so
this doesn't hold for links, right?
This does not hold for links, although I haven't thought so much about the link case, but that's correct. It does not at least obviously hold. Okay. So let me say, so our actual argument does not involve steps 1 or 2. It does involve step 3. And we wanted to sort of avoid technical pitfalls. So what we actually did was construct, maybe I need more space, since I know the bottom is full. Let's see. The argument in place of 1 and 2 is to construct an isomorphism between the Legendrian contact homology of lambda k union lambda p and some sort of homology, which we call string homology, which is the constructed, so this is constructed from chains on the path space, so chains of paths or loops, if you like, in the union of those three Lagrangians, so F union R3 union LK. So you can look at paths in this space or loops in this space and consider just singular chains in that thing. And there's the usual singular differential, but there's an additional differential that comes from some sort of string coproduct with strange differential. Coming from string coproduct. So how does this isomorphism work? So we do it on the chain level. So that is to say, to a Rabe chord for the union of these two, we want to associate some sort of chain of paths in here. And the way that that works is a Rabe chord is up at infinity somewhere. And then one looks at holomorphic disks that are asymptotic to that Rabe chord and have boundary on the union of these three Lagrangians. And consider the moduli spaces of such things. And that gives you some sort of chain in this path space. But there's some strange degeneration because this is, the union of these three Lagrangians is not smooth, and so there's some weird degenerations that happen at the clean intersection between the various Lagrangians, and that's what gives rise to this string coproduct differential.
You have singular Lagrangian, you have this algebra which is, or category which describes this shifts in microlocal support. This is the same guy?
This is supposed to be the same guy, although we didn't check that, but that's, morally speaking, that is correct. Yes. Yeah.
Is this a kind of Kovar construction differential?
Is
the
this
coproduct?
Yes.
And you get
yes.
an algebra, a differential-graded algebra.
Indeed, yes, that's right.
And it said, do you construct a quasi-isomorphism at the same level?
We do. In fact, the quasi-isomorphism we can only prove is a quasi-isomorphism in low degree or something, because they're sort of terrible transversality issues that occur higher up. But that's good enough for these purposes. Yes?
Can you just say one more time what you sent the Rabe chord to?
Yes. So you consider the moduli space of holomorphic disks that are asymptotic to the Rabe chord and have boundary on the union of these three.
Correct.
So to each such disk, you can look at its boundary. So that gives you some sort of path in these Lagrangians, and then you take the collection of all such paths over everything in the moduli space.
Okay, great. Sorry.
Okay, and again, this is I apologize that this sounds very vague, but I was trying to compress so that we can talk about some other things. Okay, so that's I think that's all I wanted to say, unless there are other questions about this result that this sort of enhanced knot contact homology completely determines the knots. Okay. All right, great. So we have a complete knot invariant.
So how do you do what counts of results here?
Oh, it's the same. Right. So I didn't tell you what the string homology was, but you can extract from that string homology again the same data. So the group ring of pi1, along with these two important pieces.
Yeah. I have another question. Does this mean that the homology coalgebra from this coproduct determined the knot, or not quite?
The homology from this from this coproduct, I think it does not quite.
Okay.
Okay, so fine. This is some sort of invariant. So what I'm maybe more interested in talking about here is how this relates to other things that you might be interested in. So it's what does it have to do with? So eventually I want to get to what does it have to do with topological strings and Humphrey polynomials. So maybe what I'll do is I'll just retrench a little bit and just go back to, so let's just return to normal context homology. Okay, so what is this? This is LCH star of lambda k, where, I already wrote this, but this is the conormal to k sitting inside of ST star R3. And I think now I'm going to relax my restriction that k is a knot. So k can be a link. R3. So firstly, let's just think for a second about what sort of object this is. So this is the homology of some differential graded algebra. And this differential graded algebra, so the first question is, what is the coefficient ring here? This will be important to us going forward. So remember, A is an algebra over Z brackets H2 V lambda. V is now this, and lambda is that. So first question, so elementary topological question, what is H relative H2? So it's easy to check that this Legendrian torus or union of Legendrian tori is null homologous inside of V. So lambda k is null homologous. Oh, I should say, so V topologically, so this is the unit cotangent bundle, so topologically this is R3 cross S2. So it does have non-trivial H2, but this Lagrangian torus, Legendrian torus, sorry, is actually null homologous. And that tells you that this relative homology splits. So in this case, this is isomorphic to H2 of V, which is R3 cross S2. I'll just write as V. Direct sum with H1 of lambda. Okay, H2 of V, that's just Z, right? And H1 of lambda, so lambda is a union of some number of tori, two tori, so this is just Z squared to the number of components. Just for simplicity, I'm going to assume in this right here, let's just assume for a second that k is a knot. Otherwise, if it's an R component link, then it's Z plus Z to the 2R. I'm going to pick generators for this Z and Z squared. The generators I will call, so generated Q, capital Q for this Z factor. This is eventually going to turn into some sort of Kähler parameter in the result manifold. And Z squared will be generated by, so remember that if K is a knot, then lambda is the unit conormal of K. So that looks like the boundary of a tubular neighborhood of the knot. So it has two distinguished classes. It has a longitude and a meridian. And so those are going to be my two generators here. Okay, and I am going to think about this group multiplicatively. So Q, lambda, and mu are multiplicative generators. I think tomorrow I'll actually undo that and write them as e to the something. I think this is okay. So what this means is that the coefficient ring ZH2 of V lambda is now just Laurent polynomials in three variables. It doesn't matter what. This. That's for K being a knot. So if K is an R component link, then instead of this you get R longitudes and meridians, and still the Q. And I lost a parenthesis. Great. Okay. So great. So we have non-contact homology is the homology of some differential graded algebra. That algebra is over this particular coefficient ring, and there's a result. So this is. From 2011, is that there exists a combinatorial formula for the differential graded algebra AD, whose homology is this Legendrian contact homology. So by combinatorial, I mean, so the way that we present it is if you give us a knot or link as the closure of some sort of braid, then there's an explicit formula for the generators and the differential. And in fact, maybe it's a good idea for me to give you some examples. But before I do some examples, let me just say that I have not been talking about degrees, but the way this is set up, this combinatorial formula. Actually, this part I'm going to say it just relies on the geometry of rate chords. So this is all of the rate chords are in non-negative degrees. So this is supported in degree at least 0. Not that the formula is supported. So and it's supported in degrees at least 0. Oh, and one other piece of notation. Once in a while, I will actually identify this DJ with the knot that it comes from. But I will also not be completely consistent about this. So if you see a K, that's supposed to represent the knot. Okay. So 2 examples. So the first one is the unknots. I'll write as U. And here I can tell you, so the reason I haven't given you this combinatorial formula is it's a little bit gross to write down. But here I can tell you exactly what is going on. So I'm going to give this coefficient ring a name. So write R for the coefficient ring. So that's for knots. This is this. Okay, and for the unknot U, so this is an algebra over R, and it's freely generated by 2 generators, which for historical reasons we call C and E. So C and E are in degrees 1 and 2. And the differential on this algebra is completely determined by where it sends C and E. And so the differential of E is 0. And the differential of C, so you would think, well, there's nothing in degree 0, so the differential should also be 0. But there actually is something in degree 0, right? This entire coefficient ring is in degree 0. And in fact, there are 4 terms of the differential of C corresponding to 4 holomorphic, well, let me write that. So this corresponds to 4 holomorphic disks whose positive end is at C and has no negative ends. And they happen to sit in 4 different relative homology classes. So that is the unknot. The other example I want to give, this, thought about whether it's actually a good idea to write this down, but it doesn't take too long, so let me just do it. So the algebra for the trefoil has more generators. Of which I will only be interested in 3 of them, so I'll write them as A, C1, and C2. These are in degrees 0, 1, and 1. And the differential of these is as follows. So the differential of A is 0. There definitely isn't anything in degree -1, so the differential of A has to be 0. The differential of C1, these are not important at all, but just to give you some sense for what these things look like. So there are 4 terms in the differential of C1 corresponding to 4 holomorphic disks whose positive end is at C1. And it looks like one of them has 2 negative ends, both at this rate chord A. One of them has just 1 negative end, and 2 of them have none. And they're at various homology classes. Again, this is sort of debatable utility writing these down though, so. The differential of C2 also similarly has 4 terms, and they look like that. Okay. And there's more generators and more differentials, but again, these are the ones that will matter. Okay.
Is it possible, at least for the case of the unknown, to sort of draw a schematic picture of the sort of plural towards the unknown that's making it clear?
Yeah, well,
where that DC is coming from?
I don't know if this will make it clear, but I can draw you a picture.
Okay, thanks.
Okay. So, whoa. So the picture is the front projection of lambda u. So lambda u sits inside of, so lambda u itself sits inside of the one jet space of S2. This is T star S2 crossed with R, and the front projection sits inside of just S2 cross R. So it's just the one jet of the thing that I'm about to draw. So S2 cross R, let's think of that as S2. Here's S2. And just take a little thick neighborhood of it, and that'll be the R direction. So I can draw it for you what the front looks like. So the front is a 2-to-1, generically 2-to-1 map lying over S2, and it looks something like this. So this is after it's been a little bit perturbed, the unknot. So if you just take the flat circle unknot, then it doesn't quite look like this, but when you perturb it a little bit, it will look like this. So this is lambda u. And in the front projection, then rate chords corresponds to critical points of differences between the local functions. So if you think of, so over everywhere except for the north and south pole, there are 2 sheets. And these sheets are locally given as the one jets of functions. If you take the difference between the functions, then critical points of that are the rate chords. And the rate chords in this case, if you perturb it a little bit to get rid of this S1 symmetry, then there will be 2 of them. There's one that maybe is here and one that's here. And those are what I'm writing as C and E. This just corresponds to the 2 critical points of the standard Morse function on S1, just shifted up by 1. And then, what a holomorphic disk, so I can draw for you what the holomorphic disks look like when you project them into here. 2 of them go like this. So there's a positive end, there's an end at C, and then they follow along the boundary of this Legendrian, and then they dive into this conical singularity. So how do you see that there are 2 of them? Well, the issue is that this picture is still not generic enough to be able to calculate things because there's this weird conical singularity. So if you perturb this a little bit, you get some sort of 4-cusp thing, and then you can actually see that there are 2 different ways to go into here. So 2 of them go up, there are 2 of them that go down. And those are those 4 disks. 2 of these, and 2 of these in the differential of C. Okay. All right. So let's do some other questions. Okay. Let's do a little bit of algebra. Or what? fastest for algebra in my world. So let's talk about augmentations. And I will be a little bit more general than what we've been doing so far. So let's just say, so let's suppose that we have, this is some sort of differential graded algebra over a ring R. So the notation is not coincidental. So in our case, the ring actually is this thing that I'm writing as R. But for this definition, this is going to be more general. And let S be a unital ring. So an augmentation of AD is a graded algebra map, a graded differential graded algebra map. Oh, graded showed up twice. Okay, let's just say graded algebra map involving differentials. So I'll write it as epsilon, and it's going to go from this differential graded algebra to the differential graded algebra S with the zero differential. And how is this graded? So I'm going to say that the entirety of S is in degree 0. So in degree 0. In other words, what does this mean? This is an algebra map from A to S, such that two things hold. So one of them, the most important one, is that it kills the image of the differential on A. So that's the fact that it maps it to the zero differential here. And then the other thing, the degree part, is so epsilon of A is equal to 0 unless A has degree 0. And finally, this differential graded algebra has a unit in it, which is the unit in R, and that needs to be set to 1. Okay, so this is one. So Legendrian contact homology. This is this homology of this differential graded algebra. This is not nice in the sense that this algebra is in general enormous, but it is sort of nice in the sense that the algebra has a multiplicative structure, and so this is somehow leveraging that. Okay. Great. So this is a purely algebraic object. The relation to geometry is that these will often come from what are called exact fillings, so I'll talk more about those in a bit, possibly today, we'll see. Probably not. Let me just note, this is fairly similar. So this induces a map on the homology. So if this is the DGA for Legendrian contact homology, then this actually gives a map from the homology to S. So this induces maps from the homology to S. That is clear, I think. And it also induces, so more importantly for our purposes, it induces a map epsilon restricted to the coefficient ring from R to S. So to ring homomorphism. Okay, because the coefficient ring sits in degree 0, so epsilon will have to send it to something. So now let's bring in the circumstance that we're actually interested in. So let's say that K is not. This works for links as well. I'll say something about the case in a second. But just for ease of terminology, so let's say that K is a knot in R3, and so this gives us AK dk, that's the DGA, over this particular coefficient ring. So the augmentation variety of K. So I'll write it as VK. And it is the set of restrictions of augmentations to R. So it's down, so epsilon restricted to R. Sorry, all my epsilons look the same. This is a different epsilon. This is an element of RS. And maybe since I've drawn a vertical line, let me not draw another one. So such that epsilon is some augmentation from this to this is an augmentation. And why am I, well, this is okay. Yeah. I don't have this in my notes, but maybe I'm going to specialize to S as just the complexes at this point. You could do this for any unital ring, but for some reason I'm going to use the complexes.
So is it the same as a local system on Lagrangian filling?
It is the it is the same as a. It is close. So there are particular. Let's see. Rank 1 local system. So I believe that not all of these actually come from Lagrangian filling. So it's but if you have a rank 1 local system, then I agree that you get something inside of here. Again, this is just some sort of algebraic thing. And this is actually a little bit of a lie, so I'll say what I actually mean by this in a second. But so, oops, I just erased I just erased it again. So let's just note that hom from R to C. So R is equal to this, and this is the same thing as C star. So everything except for 0 cubed. All right, because a map from R to C is determined by where it sends lambda, mu, and q, and it has to send them to complex numbers that are non-zero. All right, so what that means is that if you're looking at the set of all possible maps from R to C, so this sits inside of C star. And here is where I say that this is how I think of the augmentation variety, but this can have weird components of different dimensions. So what we actually do is BK is the maximal dimensional, so the closure of the maximal dimensional parts components. And once you get this, then VK is a complex algebraic variety. No. In this case. Okay, and
Is there only one maximal dimension?
there can be more than one maximal dimensional component, so you take the unions of all of them. Yeah, I'll give you examples here in a second, although the examples I'll give you only have one component. Yeah. So just to keep the link part in mind, so if K instead has R components, then BK sits inside of C star to 2R plus 1. All right, there are R longitudes, R meridians, and then Q. So that's 2R plus 1 things. I think I want to leave that in there.
So in this example, in two examples, this dependence on Q is linear, Is Q somehow special?
That is a law of small numbers thing. So if I wrote down more complicated differential DGAs, then the dependence on Q might not be linear. It just happens to be in this case. So here's an observation, which maybe I'll call an empirical observation, slash conjecture slash thing that we sort of know how to prove. And this is, so VK sits inside of C star to the 2R plus 1. And the coordinates on there are a bunch of longitudes and meridians, and then this Q variable. So if we fix Q, so for fixed Q in star, you can look at this VK. So VK now sits inside of, if you take a fixed Q slice, and then it now sits inside of C to the 2R, C star to the 2R. And VK is now, here's the observation. So this is a complex Lagrangian in C star the 2R. Lagrangian with respect to what? To the symplectic form, which is, this is probably not unexpected. And we'll talk next time about why this ought to be true. But it was surprising to me, at least the first time that I was asked whether this should be true, and just ran some examples, and indeed it seemed to be true. So in particular, so striking. So in particular, and the reason this will be true is, in fact, there's some sort of way to parameterize this locally using some sort of Gromov-Witten potential. So we'll get to this next time, but in particular, if K is a knot. So what this says is that for fixed Q, VK is Lagrangian inside of C star squared, so that means it's complex one-dimensional. So if you let K vary, then this becomes complex codimension 1. So VK, if you don't fix this, so this inside of here is codimension 1. Okay, so let's just accept that this may be true, and then use this to define the following, and then I'll give a calculation and that'll be it. So the definition is the augmentation. So if it's codimension 1, a complex algebraic variety, so it's just determined by a polynomial. So the augmentation polynomial. This is specifically for K as a knot. The augmentation polynomial of K, so I'll write it as aug K of lambda Q, so this sits inside of, it's a polynomial in these with complex coefficients. Actually, it turns out to have integer coefficients, but complex would do for us. Whose vanishing locus is this thing. So.
It's defined up to monomial, yeah?
It's defined, that's correct. So it's the minimal polynomial, and it's defined up to units inside of here. That's right. Sorry, not in here, in Laurent polynomials. In other words, just multiplication by powers of lambda mu and q. Okay. So let me just close by telling you what the augmentation polynomials are for those two particular knots. And then next time we'll see what this all has to do with topological strings, hopefully. Well, if we have an augmentation of this particular DGA, then that means that the differential of C has to be mapped to 0. So you have to choose Q, lambda, mu so that 4-term thing gets set to 0. And that is just to say that the augmentation polynomial for U is just Q minus lambda minus mu. Whoops. So to calculate the augmentation polynomial for the trefoil, by the way, this is the right-handed trefoil. I didn't write that down anywhere, but it actually depends on chirality. What we have to do is we have to send q, lambda, and mu to complex numbers, and also send this A generator to some complex number, so that these are both 0. So what that means is that we need to find what are the values of q, lambda, and mu, so that these two polynomials, if you think of them as polynomials in A, they have a common root. Right, so Vt is the set of q, lambda, and mu, such that dc1 and dc2 have a common root in the variable A. And this is an easy, there's a name for this. This is the resultant of those two polynomials. So if you just take the resultant of those two polynomials, you get something. I'll write it down, but again, it's not particularly important, but just so you can see that it's not the smallest of things. Okay, something like this. And for more general knots, calculating the augmentation polynomial boils down to some sort of algebraic problem in elimination theory where you have some number of variables and also these coefficients q, lambda, and mu, and you want to know when do these polynomials in this collection of variables have a common root. So in this case, it was a common root in 0 variables. Here it was a common root in 1 variable, this A. And in general, it's more complicated, but it's at least in theory computable. Okay, so I think this is a good place to stop. And then tomorrow I'll talk about what this augmentation variety means and what it has to do with the Hopfli polynomial.
Any questions?
Maybe just a small remark. This is a way to formulate it completely without any homological disks. Maybe you do the following. You have this Lagrangian Legendary submanifold in quadrant and spherical potential bundle, yeah, apply it for very long kind of gradient plot, so the things will be project that over through get something around a huge sphere. And now consider the neighborhood of this guy and use it shifts and macro to support on these things, and then how to use Q, you modify by B field and second homology plus. It will completely elementary story without any homomorphic disks whatsoever.
That's actually really nice. So we knew that for Q equals 1. So without the Q, I think we knew this, but there was some sort of question of how you
because if you remove kind of 0, you consider only neighborhood, and then you can modify by second homology plus.
Right.
Completely elementary story.
Yeah, that sounds correct. I should probably talk with you more about this, but yes.
Any other questions or remarks? Well, thank you. We'll be back.